All right, good afternoon. So I already recorded this lecture, but for some reason the audio was really messed up and it sounded like I was really far away. So we're doing it again. So today we're going to be talking about the derivative as a function. So we already know that we can take the derivative at a point, and our current definition for the derivative of a function f at a fixed point a is f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a all over h. But we can let a vary. That is, we can let a take on any value we want. Maybe a is equal to 1, maybe it's equal to 10, maybe it's equal to 100. We can let it take on any value we want. And we can represent this variance by replacing a with the variable x and rewriting equation 1 as f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, though it may not seem like it, f prime is a function, and it's called the derivative of f, and it can be geometrically interpreted as the slope of the line tangent to the graph of f at a point x comma f of x. So we can put in a function into our derivative and get out another function, and that's exactly what we're after. So let's work on an example really quickly. So I want you to find the derivative of f of x equals negative x squared plus 6x. And I'm actually going to do something a little bit different this time, and I'm going to work through this example with you instead of having all the lines already posted ahead of time. So to solve this problem, we're going to begin with the definition of our derivative, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. So our first step is going to be to fill in f of x plus h. So the limit, and then we have negative x plus h quantity squared plus 6 times x plus h minus negative x squared plus 6x all over h. Expanding out our first and second term, we get negative x squared plus 2xh plus h squared plus 6x plus 6h plus x squared minus 6x all over h. Grouping together like terms, we see we have a negative x squared and a positive x squared minus 2xh plus h squared, positive 6x minus 6x plus 6h all over h. So we can see already that our first term, x squared, and our second term, negative x squared, are going to cancel. Our 6x and negative 6x are going to cancel. So we're left with, let me scroll down, f prime of x equals the limit as h approaches 0 of negative 2xh plus h squared plus 6h all over h. You've probably noticed that we can definitely factor out an h in this case. And if we factor out an h from the numerator, we can divide it by the h in the denominator and get 1. So we're left with h over h times negative 2x plus h plus 6. H over h goes to 1. Now we're ready to take our limit. So as h goes to 0, well, we've only got one term that depends on h. That's going to go to 0. We're going to be left with negative 2x plus 6. So in this case, we put a function in. We put in negative x squared plus 6x, and we got out another function, which is negative 2x plus 6. And later on in the course, we're going to develop a technique that's going to make it easier for you to check these answers and actually make it easier for you to compute these answers in the first place, but that's neither here nor there. So now let's comment on notation a little bit. Capital delta means the change in. So capital delta x means the change in x, and it's computed to be delta x equals x2 minus x1. And the same goes for delta y, except this time we're evaluating f of x2 minus f of x1. And often f prime of x is denoted as the limit as delta x goes to 0 of delta y divided by delta x. And in fact, f prime is represented in many ways, all of which you'll become familiar with. We can use f prime of x, y prime, dy dx, df dx, and finally d dx of f of x. And d in this case is akin to that delta. So dx is akin to delta x. And later on in this course, when we talk about going the opposite direction from differentiation, we'll discover why we can use dx instead of delta x. So that's a little bonus content for later. So let's do another example. Let y equal the square root of x and compute dy dx. So we just saw in the previous slide that dy dx is another name for f prime of x, is another name for the derivative. What I'm asking you to do in this question is to compute the derivative of the function f of x equals square root of x. So let's go ahead and do that. We're going to start with our definition. Dy dx equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So our first step is going to be to fill in our function f of x and f of x plus h. So x plus h square root minus f of x, which is just x, all over h. Now when we see a square root, we know exactly what to do. We're going to multiply it by something divided by itself, and that something is going to be square root x plus h plus square root x over itself, which is x plus h square root plus square root x. Well, when we do that, our numerator becomes x plus h minus x over h times square root of x plus h plus square root of x. Now it's easy to see that our x's are going to cancel, and then we've got h divided by h, that's going to turn into 1, that's going to cancel. So we're really interested in the limit as h approaches 0. I'll try not to be sloppy in my work. Of square root x plus h plus square root x, all in our denominator. Now when we take our limit, this h is going to go to 0. We're left with 1 over root x plus root x. Our final answer is 1 over 2 root x. And there you have it. We plugged in a function and we got another function out, and that's exactly what we're looking for. So now we're going to talk about some important things. A function f we say is differentiable at a point A if f prime of A exists. It is differentiable on an open interval if it is differentiable at every point in the interval. So if this is my line, maybe I have 0, maybe I have 1, and somewhere in between there, I've got a point A. And if it's differentiable at A, f prime of A must exist there. And for it to be differentiable at B, f prime of A must exist there, or sorry, f prime of B must exist there. And if it's differentiable at all the points in between 0 and 1, then we say it's differentiable on the interval 0, 1. So here's a final theorem, and this is actually kind of a big deal. If f is differentiable at A, then f is continuous at A. But beware, the converse is not true. There are functions that are continuous but not differentiable. And we say that because there's functions like the absolute value of x or the negative absolute value of x. We can't differentiate them the same way that we expect to, nor do we expect to get an answer. So this theorem is very important. If you're a student that's studying mathematics for the rest of your degree program, then this is going to come up again and again and again, and it's going to be very important. So that's it for me. Good luck on your exams. I'll see you in the next video.